strands of cooler molecular hydrogen stretch across several light years. These strands are made up of hydrogen without methane, ethane, or water, adding yet another mysterious layer to this stunning cosmic scene. As we move farther out, we come across the center of the Orion Nebula, which is covered by a huge cloud of cooler, denser gas. This cloud interacts with the bright stars and the glowing hydrogen, creating a beautiful display of light in many colors. Hidden behind this curtain are hundreds of objects in space that cannot be seen with the naked eye. However, with the help of infrared cameras and modern telescopes, we can look through this cosmic fog. By combining data from different sources, astronomers have found about 700 protostars at different stages of development in this area. These stars are spread out more sparsely than in the nebula's center because of the weaker pull of gravity from the surrounding gas. Most of these objects are still very young in cosmic terms and are still forming. According to current ideas about star development, new stars are created through the slow collapse of large clouds of space gas. As this happens, large nebulae break up into smaller, tightly packed areas that soon become protostars. These groups of young stars are called stellar nurseries, or, more scientifically, regions of star formation. At some point, the internal pressure of the gas becomes so strong that it balances the pull of gravity, bringing the protostar into a temporary state of balance. Meanwhile, the remaining gas forms a large spinning disk. Some of this material is pulled into the forming star, while the rest is pushed far beyond the star's reach. The young star's growing magnetic field also plays a role in this process. As charged particles are pulled along the magnetic lines, they speed up and are eventually thrown out at incredible speeds. These flows can reach up to several hundred kilometers per second, and when they crash into nearby gas clouds, they create swirling whirlpools and half-spheres called Herbig-Haro objects. These objects are not only interesting because of their size and movement, but they also produce light and heat as energy is released during the collisions. The high-speed movement of the gas also causes shock waves to spread through the surrounding material, which can be detected by telescopes. Since stellar nurseries contain many closely spaced protostars, each releasing gas in different ways, it's no surprise that Herbig-Haro objects come in many shapes and colors. They are often the result of large cosmic interactions, making them very unstable and unpredictable. These objects change color and shape quickly, usually disappearing entirely over tens of thousands of years. During this time, they can travel anywhere from 1 to 3 light years from their parent stars. So far, about 400 such objects have been found, but the total number in the Milky Way is thought to be around 150,000. One clear example of this phenomenon can be seen in the Orion Nebula, where huge bullets of gas, each hundreds of astronomical units across, are moving at amazing speeds. These bullets can cut through thinner hydrogen clouds, creating shock waves that stretch out across the nebula. Spectral analysis shows that the tips of these bullets contain glowing iron atoms in the infrared spectrum. These bullets are thought to be about 1,000 years old, and their origin is still a mystery, possibly linked to some kind of disaster. Beyond the Orion Nebula, we discover that it is part of a much larger cosmic structure called the Orion Molecular Cloud. This huge region stretches for hundreds of light years and covers much of the Orion constellation we see in the night sky. One of its many interesting features is the Hubble's Head Nebula, a dense cloud of dust about 3.5 light years across. The nebula stands out against a background of red light. Not far from the Orion Nebula is the Barnard Loop, a giant nebula formed by a series of supernova explosions that happened about 3 million years ago. The shock waves from these explosions mixed with the surrounding gas, forming a huge, curved nebula that glows red from the energy of nearby young stars. Despite its beauty, the Orion Nebula is a delicate and unstable structure by cosmic standards. Stellar winds, the pressure from the light given off by the young stars, and the turbulent gas emissions constantly push and spread out the material that makes up the nebula. It has already lost about 60% of its original mass, and in about 100,000 years, the nebula will no longer exist in its current form. Instead, a group of stars, similar to the Pleiades, will remain. For a while, these stars will move together as a group, but eventually each star will travel in its direction, continuing its journey through the vast expanse of the galaxy. The first stop on our journey takes us 202 light-years away from Earth to a star known as K211, an orange dwarf. This star has about 7 times the mass of our Sun, but its radius is only 68% that of the Sun. Despite the differences, the star's temperature is around 4,600 Kelvin, which is about 20% cooler than our Sun. Now let's focus on the planet K2-141b, located just 0.007 astronomical units from its star. This planet is truly strange. It's a rocky exoplanet, about 5 times heavier than Earth, with a radius of 1.5 times that of our planet. Because of its size and mass, we can expect the gravity on K2-141b to be at least twice as strong as Earth's. Its dense, metallic core makes up a significant portion of the planet's mass, around 20 to 50%. The planet takes just 6.5 hours to complete an orbit around its star. This close distance causes the planet to be tidally locked, meaning one side always faces the star, while the other side remains in perpetual darkness. On the day side, temperatures soar to a scorching 3,270 K, around 3,000 degrees Celsius, hot enough to melt most rocks and metals and even cause them to vaporize. Scientists believe the day side is covered by a vast ocean of molten lava that's always bubbling and churning. The atmosphere of K2-141d is unlike anything we know, composed of steams made up of heavy metals and silicates. On the opposite side, the night side of the planet is cold, with temperatures plunging tens of times lower than those on the day side. The temperature on the night side is believed to be well below freezing. This extreme temperature difference between the day and night sides creates incredibly strong winds, reaching speeds of up to 1.75 km/s, about 5 times the speed of sound. These powerful gusts whip across the planet's surface, creating deafening, rumbling sounds that never stop. The planet is a constantly shaking, turbulent world where the weather alone would be enough to overwhelm any earthly senses. It's believed that on the night side of this planet, the gases in the air start to cool and form droplets, which fall to the surface as burning rain. This rain creates rivers of lava, and over time, these hot rivers cool, causing metals to sink back into a molten sea beneath the surface. From there, they eventually turn into gas again, continuing this amazing cycle of heat and energy. However, this strong process only happens on a small part of the night side. The problem is that the gases from the planet's hot day side don't reach the main part of the night side. Instead, they fall near the border, meaning the central night side is probably a frozen desert covered in thick layers of solid rock. Interestingly, K2-141b is not even the hottest planet we know. For comparison, there's another planet, Kelt 9b, located about 670 light-years away, whose surface temperature reaches an amazing 4,600 Kelvin, about 4,830 degrees Celsius. In contrast, the outer layers of most red dwarf stars are much cooler than this planet's surface. This shows just how incredibly hot Kelt 9b is. It's similar in temperature to some stars. Kelt 9b orbits a star called Kelt 9, which is much bigger and hotter than our Sun. Kelt 9 has a whitish-blue color and is 2.6 times as heavy and 2.3 times as wide as the Sun. Its surface temperature is around 10,170 Kelvin, or a very hot 99,900 degrees Celsius. These extreme conditions are partly because Kelt 9b orbits its parent star very closely, only 0.35 times the distance between Earth and the Sun. The planet completes one full orbit in just 1.5 days. Kelt 9b is a gas giant, much like Jupiter, but it's much heavier, almost 3 times as heavy, and its size is about twice as large. Based on what we know about gas giants, it's believed that the inner atmosphere of Kelt 9b could be even hotter, with temperatures reaching as high as 11,000 Kelvin. This intense heat is caused by the ionization of heavy metals in the planet's atmosphere. The conditions on Kelt 9b are truly extreme, far beyond anything we experience on Earth. The atmosphere of this distant planet contains unusual elements like vaporized iron and titanium, in addition to the more familiar components such as hydrogen and helium. Its close orbit around a parent star and the intense heat has caused the planet to gradually lose its atmosphere. Over time, powerful stellar winds blow the atmosphere away into space, which is why the planet is surrounded by a cloud of thin, rarefied gas. This gas will eventually be pulled back in and absorbed by the star. Interestingly, some studies suggest that the planet loses up to 68 times the mass of Earth every billion years. If this continues, the planet might eventually lose all its atmosphere and turn into a barren, rocky world. However, this process might take a very long time, and the parent star is likely to reach the final stages of its life. Before then, eventually swallowing everything within its reach, including the planet. This is a stark reminder that stars don't just warm planets, they can also destroy them. Other celestial bodies in the universe have already felt the full wrath of their parent stars. One such object is located 4,570 light-years from Earth, orbiting a small star called V391 Pegasi. This star is a white dwarf, about half the mass of our Sun and only about 23% of its size. Its surface temperature is incredibly hot, nearly 30,000 Kelvin. By now, all the thermonuclear reactions inside the star have stopped, and it's slowly cooling down. Eventually, it will transform into a black dwarf over the next hundreds of billions of years. The planet orbiting V391 Pegasi, known as V391 Pegasi b, has an extraordinary history. Mathematical models suggest that this planet not only survived the star shedding its outer, but came dangerously close to being engulfed by the star itself. When the star expanded into a red giant, its outer layers, extremely thin by then, nearly touched the planet's orbit. Despite the vast difference in density between the star's layers and the planet's atmosphere, the planet didn't get destroyed instantly. It slowly lost speed and began spiraling inward toward the hotter, denser layers of the star. However, before it could be completely consumed, the star shed its outer layers and the planet managed to survive. Today, V391 Pegasi b is a gas giant about 3 times the size of Jupiter. It orbits the star at a distance of 1.7 astronomical units and takes around 1,170 Earth days to complete one orbit. It's unclear how the planet was able to retain such a large mass after being so close to the star's scorching layers. The star's transformation caused significant changes to the planet's orbit and physical characteristics, but the planet's past before it came into contact with the star's plasma remains a mystery. The universe is filled with objects that possess strange and even mind-boggling characteristics, many of which are invisible to regular telescopes, but detectable through radio waves. Pulsars, for example, are neutron stars that spin incredibly fast, emitting regular bursts of electromagnetic radiation. One such pulsar, located about 4,000 light-years from Earth, has a particularly intriguing set of features. Its diameter is just 20 kilometers, and its mass is 1.4 times that of the Sun. It spins at an astonishing rate, around 10,000 rotations per minute, while emitting powerful radiation beams. Nearby, there's a planet in orbit around this pulsar. The surface of this planet is constantly bombarded by these lethal radiation pulses, making it an extremely hostile place. The planet completes a full orbit around the pulsar in just 2 hours, and it orbits at a distance even smaller than the Sun's radius, only 600,000 kilometers away. The planet's mass is about 330 times that of Earth, and its radius is 4 times larger than Earth's. This results in gravity 20 times stronger than on Earth. The planet's density is extraordinary, about 23 grams per cubic centimeter, denser than most known substances. It's believed that the planet is largely made of crystallized carbon, with some oxygen bound to the carbon. It seems unlikely that this planet could have survived a supernova event. More realistically, the planet probably formed after the star went through its life cycle and turned into a pulsar. It may have been a leftover piece of debris from a white dwarf, a remnant of a dying star whose material scattered across space. Regardless of its origin, this world remains one of the most dangerous and uninhabitable places in the universe. About 650 light-years from Earth, there is a huge red giant star called IRC Plumosnoso 2116, or CW Leonis. This giant star is incredibly large. At its biggest size, its radius grows to about 560 times that of the Sun, which is around 2.6 times the distance between Earth and the Sun. If CW Leonis were at the center of our solar system, it would easily cover planets up to Mars, with its outer edges reaching the inner part of the asteroid belt. Surprisingly, despite its enormous size, CW Leonis isn't very heavy. Its mass is estimated to be between 1.5 and 4 times that of the Sun. Its surface is not as hot as most stars, with a temperature of around 2,300 Kelvin, about 2,000 degrees Celsius. However, its great size allows it to give off about 8,500 times more energy than the Sun. Like other red giants, CW Leonis is nearing the end of its life. Scientists think the star is several billion years old. Long ago, it was probably a bright blue-white star with a mass 3 to 5 times greater than the Sun. Over time, most of its hydrogen fuel burned out, turning into helium that gathered in the star's center. This helium pushed the remaining hydrogen outward, creating a very hot core. But this core no longer had the reactions that produced energy, starting the star's change into a red giant. The pressure inside CW Leonis made it expand greatly, causing its outer layers to become thinner and unstable. Its once bright color faded to the deep red typical of red giants. Inside, nuclear reactions still occur, producing intense pressure and heat. At one point, a major event called the helium flash happened. During this, helium atoms combined to form carbon, leading to a big rearrangement of the star's internal structure. The core became extremely hot, while the outer layers cooled and dimmed. Today, CW Leonis contains a lot of carbon, but it isn't heavy enough to support further nuclear reactions. Instead, its interior goes through cycles of cooling, shrinking, heating, and expanding. These cycles cause the star's brightness to change over 649 days. At its brightest, CW Leonis is 11,300 times brighter than the Sun, and at its dimmest, it still shines 6,250 times more brightly. When the star shrinks, some of its outer layers break away, forming a beautiful cloud of gas rich in carbon and oxygen around it. This cloud, or nebula, has been forming for at least 69,000 years and has about 1.55 times the Sun's mass. It is massive, stretching out to 84,000 astronomical units. Within this huge cloud, scientists have noticed shapes like arcs, bulges, and uneven rings, likely caused by the star's magnetic activity and winds. The chemical makeup of the nebula is especially interesting. Scientists using light analysis have found around 70 different substances, including carbon dioxide, water, and ammonia, as well as heavier elements like iron. This variety makes CW Leonis an exciting object for study, as it reveals details about the processes in dying stars. Some scientists think CW Leonis may have once had planets, but they were probably swallowed during the star's growth into a red giant. No direct evidence of these planets exists, though small movements in the star, seen in 1994 and 2017, hint at possible past interactions. Astronomers have detected strange movements in the gas and dust cloud surrounding CW Leonis, a dying red giant star. These shifts might be caused by a small, faint red dwarf orbiting the star, though efforts to detect its light have failed so far. This failure could be due to the nearby nebula, which scatters and reflects light, making it nearly impossible to identify objects in the area. If this companion star exists, it's likely much smaller than the Sun and would take about 100 years to complete one orbit around CW Leonis. Another curious feature is the surprisingly high amount of water vapor found in the star's surroundings. Initially, scientists thought the star absorbed icy comets as it expanded, melting them into water. However, in 2009, observations revealed water vapor forming in the star's upper layers at incredibly high temperatures, around 1,000 Kelvin. This discovery didn't match the existing models of red giants, which predicted that oxygen in such stars would bond with carbon to form carbon monoxide, leaving no oxygen for water formation. To explain this anomaly, researchers proposed a bold new idea. They suggested that intense ultraviolet radiation might break apart molecules like silicon oxides and carbon, freeing oxygen to combine with hydrogen and form water vapor. However, this theory raises another question. Where does the ultraviolet radiation come from? Red giants, like CW Leonis, have dense outer layers that usually block such radiation. Scientists speculate that occasional ruptures in the star's surface might allow ultraviolet rays to escape, triggering these reactions. The mass of water vapor in CW Leonis's atmosphere is staggering, several quintillion tons, though it's still a tiny fraction of the star's total mass. As a red giant, CW Leonis is nearing the end of its life. In 10,000 to 30,000 years, it will run out of fuel, eject its outer layers in a dramatic explosion, and shrink into a dense white dwarf. This leftover core will retain about 80% of the Sun's mass, but will cool and dim over billions of years, eventually fading into a cold, dark, black dwarf. Before this quiet end, the explosion will create a brief moment of cosmic fireworks. The intense heat and shock waves will forge heavy elements like gold, lead, and uranium. These elements will later scatter through space, becoming part of new stars, planets, and possibly even life. While the universe is shaped by cycles of destruction and creation, every end paves the way for a new beginning, continuing the story of cosmic evolution.
In a universe brimming with mysteries, scientists estimate that there are over 100 billion planets beyond our own solar system, many of which defy our imagination. We'll uncover the strange and extreme conditions of these distant worlds, from scorching atmospheres to relentless storms. Join us today as we dive into the atmosphere and surface climates of the scariest exoplanets in our universe. When we think of planets, our minds often go to those that orbit our sun. However, exoplanets or extrasolar planets are those intriguing worlds that exist outside our solar system. The primary defining characteristic of an exoplanet is that it must orbit a star, not just any celestial body, but one that provides the necessary gravitational pull to sustain a stable path over a significant period. Another key aspect is size. Exoplanets vary immensely in size, ranging from those smaller than Earth, known as super-Earths, to gas giants far larger than Jupiter. To be classified as an exoplanet, an object must be large enough to not be a star in its own right. This means that it must not undergo nuclear fusion in its core, which is the defining trait of stars, and instead have a solid or gaseous composition that allows it to be generally classified under its own category. Additionally, exoplanets cannot be remnants of star systems, such as brown dwarfs. They must maintain their gravitational interactions that define their status as a planet. This interaction often means they are part of a more extensive system comprising other celestial bodies, which brings us to the point that many exoplanets are found in systems with multiple planets orbiting a single star. Lastly, the methods used to detect exoplanets add to their classification. Astronomers utilize several techniques, such as the transit method, where a planet moves in front of its star, causing a slight dimming that can be measured, or the radial velocity method, which observes subtle gravitational effects of a planet on its star. Together, these characteristics and detection methods enrich our understanding of planets beyond our own celestial neighborhood, expanding our cosmic horizons. As of now, astronomers have confirmed the discovery of over 5,000 exoplanets, which are planets located outside our solar system. This number continues to grow as new missions and advanced detection techniques enhance our ability to explore the cosmos. Each of these exoplanets offers a unique glimpse into the diversity of worlds that exist in our universe, varying vastly in size, composition, and distance from their parent stars. To discover these distant planets, scientists primarily employ two main methods: the transit method and the radial velocity method. The transit method involves monitoring the brightness of stars over time. When a planet passes in front of its star, it temporarily blocks a tiny fraction of the star's light, causing a measurable dimming. This approach not only reveals the existence of the planet, but can also provide insights into its size and orbit. On the other hand, the radial velocity method detects planets by observing the gravitational pull they exert on their parent stars. As a planet orbits, it causes the star to wobble slightly. This wobble can be detected through changes in the star's light spectrum, indicating that a planet is present. Together, these methods allow astronomers to paint a more complete picture of the intriguing environments that lie beyond our solar system. As technology continues to advance, we can expect even more discoveries. Next-generation telescopes and space missions are being developed to search for exoplanets, particularly those that may harbor conditions suitable for life. The ongoing quest to understand these distant worlds not only enriches our knowledge of the universe, but also inspires deeper questions about our own planet and place in the cosmos. The classification of exoplanets hinges on several key factors that define their physical and chemical properties, helping scientists distinguish between categories like gas giants, rocky planets, and ice giants. One important aspect is the planet's composition. Gas giants, for instance, are mainly composed of hydrogen and helium, making them massive but lacking a solid surface. In contrast, rocky planets have a solid terrestrial surface and are primarily made up of materials like silicates and metals. Another significant factor is the planet's size and mass. Gas giants are typically much larger and more massive than rocky planets. Their gravity is strong enough to retain thick atmospheres of gas, which can extend hundreds or even thousands of miles into space. On the other hand, rocky planets are smaller and less massive, with a structure that supports solid landforms, mountains, and valleys. This size distinction plays a crucial role in determining their evolutionary paths and potential for hosting life. Temperature also plays a critical role in classifying exoplanets. It influences the types of materials that can exist in a gaseous or solid state on a planet's surface. Ice giants, for example, are classified as such due to their unique compositions that include significant amounts of water, ammonia, and methane in the form of ice. These planets, like Uranus and Neptune in our solar system, tend to have temperatures lower than those of gas giants, which allows for the formation of volatile compounds that differentiate them from their larger counterparts. Lastly, the environment where an exoplanet resides contributes to its classification. The distance from its host star can indicate what materials could remain in solid or gaseous forms. Planets closer to a star may lose lighter elements due to their intense heat, while those in the colder regions farther out can gather ice and gases. Each of these factors intertwines to create a fascinating tapestry of planetary diversity in the universe, highlighting the complexities of planetary formation and classification. Understanding exoplanets, or planets outside our solar system, is significantly impacted by their distance from Earth. The farther away an exoplanet is, the fainter it appears, which makes observation a challenge. Telescopes must be equipped to capture light from these distant worlds, and as the distance increases, So too does the difficulty in gathering enough light to analyze the planet's atmosphere, size, and orbital characteristics. Additionally, the distance affects the methods we use to discover these planets. For instance, the transit method, which observes the dimming of a star's light as a planet passes in front, works best with nearby stars. The light from nearer stars is more intense, allowing for more precise measurements of the star's brightness changes. When we try to apply this method to distant stars, the faintness of their light can obscure these crucial signals, potentially leading to missed discoveries. Meanwhile, the radial velocity method, which measures the gravitational tug a planet exerts on its star, is also influenced by distance. Closer stars produce more noticeable shifts in their light due to the wobbling effect caused by orbiting planets. Therefore, exploring systems within a certain proximity offers a greater chance of detecting and confirming the existence of exoplanets. Ultimately, distance shapes our entire approach to studying exoplanets. It determines which stars we can realistically observe and influences our ability to study their properties in depth. To make sense of the cosmos and these intriguing worlds beyond our own, researchers continuously seek innovative techniques and more powerful telescopes, striving to bridge the gap between Earth and the outer reaches of our galaxy. Each discovery, regardless of distance, provides us with deeper insights into the nature of planets and the universe at large. Exoplanets, or planets beyond our solar system, have been discovered in numerous star systems across different constellations, each adding a unique piece to our understanding